Section 12.2 is continuing on with applications of the derivative and learning about the second derivative. So we're going to learn about some notation for higher derivatives. We're going to practice finding higher derivatives. Then we're going to learn about something called concavity and a point of inflection. And first we're going to look at a graph and see what they look like. And then we're going to apply the concavity test, which uses calculus. And then we're going to interpret that point of inflection as something called the point of diminishing returns. And then we're going to use the second derivative test. And you'll see that it's just another way to find local max and mins that's sometimes easier. So recall that we always read graphs from left to right. And if a function is increasing, its graph is rising, and its derivative is positive. So if the derivative is positive, the function is increasing. So that's a two-directional statement. If the derivative is positive, the function is increasing. If the function is increasing, its derivative is positive. So this is f prime greater than 0. So then we also know that the opposite is true, that if the function is falling from left to right, then we say it's decreasing, and if the derivative is negative, the function is decreasing, and if the function is decreasing, its derivative is negative. If the function we're examining is a revenue function, then it would be important to know whether it's increasing or decreasing, but the first derivative can't tell us how fast or how quickly it's increasing or decreasing. So that's what we need the second derivative for. The second derivative tells us the rate of increase. It's the derivative of the derivative. So let me write an analogy here for you. R prime is to R as R double prime is to R prime. So everything that R prime tells you about R, then R double prime tells you that about R prime. So we know if R prime is positive, that means R is increasing. So the analogy says that if R double prime is positive, then R prime is increasing. And the opposite's also going to be true. So if the first derivative is positive and the second derivative is positive, then the graph is going to look something like this, and the function is increasing at an increasing rate. So this is R prime is positive and R double prime is positive. So if the first derivative is positive and the function is increasing, well, there's another way that can happen, and that's if the second derivative is negative, and then our function will look something like this, where it's still increasing, but it's increasing at a decreasing rate. Whatever's happening is slowing down. It's increasing less and less. Okay, so now let's look at what if the first derivative is negative, so the function's decreasing, and the second derivative is positive. So here we have the first derivative is negative, and the second derivative is positive, and we look at the picture and we say the function is decreasing, but at a decreasing rate. If this was a hill you were riding a sled on, the sled's going to slow down. And then we have one more combination. If the first derivative is negative and the second derivative is negative, so this is first derivative is negative and second derivative is negative, the function is decreasing at an increasing rate. If you were riding a sled down this hill, it would be speeding up. So let's put all of this information on one chart. Here is what the function looks like if r prime is positive and r double prime is negative. Then here we have r prime is positive and r double prime is positive. Then we have r prime is negative and r double prime negative, and r prime negative and r double prime positive. So those are the only four combinations. If you have two things and they each have two possible states, that gives you a total of 4 different combinations. So every graph is some combination of these 4 pieces. So if you think of any graph that we've drawn, if we look at this section right here, it's this piece. If we look at this section right here, it's this piece. And if we look at this section right here, it's this piece. And this section right here is this piece. So all the curves we've been looking at can be made from these 4 shapes. They're really the only possibilities. Okay, so there's no end to how many derivatives you can find for a function. You can just keep taking more derivatives. But for us, the second derivative is where we will stop because it has interpretation and a meaning in an application problem. Whereas if you continue taking more derivatives, then they stop having any meaning that you can interpret. So the second derivative, so when we write 1 prime, we say f prime. If we want to say the second derivative, we put 2 marks and we say f double prime. So that says take the derivative of the derivative. Then if you wanted to take another derivative, you can. And we would say f triple prime. And then after that, we don't use primes anymore. We put a little 4 in parentheses. And now we don't have any fancy terms. We just say the fourth derivative. So this notation, the d squared y dx squared, this is more needed in Math 42 where they're doing multivariable calculus. We are not doing multivariable calculus, but I wanted you to see the notation because the book sometimes mixes up the notations just to make sure you're familiar with all of them. So any of these 3 notations all mean find the second derivative. Okay, so let's do some examples. So for this function, the first derivative needs the chain rule. So the 4 would come down in the front. Don't change the inside to the new power of 3 times the derivative of the inside. So that's going to be 8 times 2x plus 1 cubed. So that's the first derivative. So then to find the second derivative, we take the derivative of the derivative. So we're going to have 8 times 3 comes down in the front, 2x plus 1 to the new power of 2 times the derivative of the inside, which is 2. So this is going to be 48 times 2x plus 1 squared. So this is the second derivative. Then the next notation, f double prime of 0, we've been practicing that with our single prime. It says put in 0 where you see x, and that's going to be 48. So when x is 0, the second derivative is 48. And when x is 2, we're going to plug 2 in for x. And that's going to give us 25 times 48, or 1200. So when x is 2, the second derivative is 1200. And then we're also asked to find f double prime of 3. So we'll have, negative 3. And interestingly, this turns out to be also 1200. Okay, so that is find the second derivative and then evaluate it at some particular values of x. So now let's look at b and notice that it's a product. It's a product of two functions. So we have the first function is the x, and the second function is the e to the 2x. So I'm going to need the product rule, and u prime is going to be 1, and v prime is going to be 2e to the 2x. So my first derivative is going to be e to the 2x plus 2x e to the 2x. And hopefully you've noticed by now that if you have an exponential and a product rule, the exponential shows up in both terms of the product rule and can be factored out. So we'd factor out e to the 2x and have 1 plus 2x, and that's our first derivative. So now we need to do the second derivative, and again I have a product. So I'm going to have the u equals the e to the 2x. The v equals the 1 plus 2x. Then u prime, 2e to the 2x. And 2 is v prime. So f double prime of x is going to be 1 plus 2x times 2e to the 2x plus 2e to the 2x. So I need to simplify this, and I see a common factor of 2e to the 2x. So I'm going to factor out 2e to the 2x and get 1 plus 2x plus 1. So that's going to be 2e to the 2x times 2x plus 2. But now I see I have a GCF of a 2. So I should also pull that out and have 4e to the 2x times x plus 1. So that's my second derivative. And then I want to evaluate the second derivative at 0. And e to the 0 is 1, so this is going to be 4. So when x is 0, the second derivative is 4. And then we want f double prime of 2. So everywhere I see an x, I'm going to put a 2. And that's going to be 12e to the 4. And this is an exact answer, so unless you're asked for the decimal approximation, give the exact answer. And last, we're asked for f double prime of negative 3. 4 times e to the 2 times negative 3 times negative 3 plus 1. So it's going to be negative 8 e to the negative 6. Okay, so I'm going to pause the movie here and start again on the next topic, which is concavity.